In this lesson, we're going to bring together everything we've built so far: vectors, parametric equations, and geometric reasoning. Our focus, one of the most fundamental questions in mathematics and in the real world: do these two paths ever meet? In 2D, this is a familiar story. Lines either intersect, are parallel, or they're the same line. But in 3D, the story gets richer because now two lines can pass each other in space and never touch, even if they're not parallel. That's called being skew, and it only happens when you step into 3 dimensions. So today we're going to explore how to find the point of intersection between two lines in 2D, not using how we would have done it in grade 9 and grade 10, but using parametric or our Cartesian forms of our equations, vector form of our equation. And how to determine if two lines in 3D intersect? Are they parallel or are they skew? By solving a system of vector parametric equations. Why does this matter? Well, it's because this is how engineers check whether structural supports align. Animators can detect collisions in 3D environments, and pilots can calculate if flight paths cross. In math, we don't just graph and hope for the best. We solve systems and let logic and structure show us the truth. So get ready to combine your algebra skills with vector reasoning and learn how to tell if two paths in space are destined to meet or destined to miss forever. So in 2 dimensions, when we have two lines that intersect, there's 3 possibilities. So they could intersect. They're going to cross each other. They're going to have one point in common. And that's what we're looking at here on this first one. So they will have one point in common. Another possibility will be that they'll be parallel. And if they're parallel, remember back, they will have the same slope. And when we're talking straight lines, they'll have the same slope, but they're never going to meet because their y-intercepts will be different. So same slope, but never meet. And the third choice here is that they are coincident. They really are the same line. So one line lies right on top of the other. In this instance, when they're coincident, they will have an infinite number of points of intersection. So there will be an infinite number of points of intersection, because all of them will be the same. They overlap. These two lines overlap each other. So we know from grade 9 and 10 how to solve these algebraically. You did a lot of it when you were trying to determine point of intersection of two straight lines. Now that we know how to write both vector and parametric equations of lines, we can solve systems of lines in 2 space a little bit differently than we did in grade 9 and 10. We're still going to use substitution or elimination. It's just that the starting equations will look a little different. So we're going to talk about all the scenarios first, and then we're going to go ahead and do some examples. So we just looked at 2D, lines in 2D. Now in 3 dimensions, we have more choices for how these lines can interact. So in 3 dimensions, lines could be intersecting, they could be parallel, they could be coincident, or they could be this new concept of skew. We're going to talk about parallel first, since this is sort of what we are familiar with, the idea of it. So when we have parallel lines in 3D, we call them parallel and distinct. So this would be parallel and distinct. And the distinct part is really just telling me there is no overlap. There's no intersections at all. So there's no intersections. So an example of how we would see this would be if I have one vector A in a vector equation with a point position vector -1, 4, 2, plus my scalar multiple of my slope or my distance vector, a -2, 2, 2. And then let's say I have a second line represented by vector B that has a position vector of 1, 3, 1, plus a scalar multiple of our direction vector, negative 2, 2, 2. Now, we can see that they share a direction vector. So they share this direction vector, but they don't have any points in common. And what I'm going to show you how to do today is to take that information when they share a direction vector and determine whether or not they're parallel or coincident. So now let's talk about coincident. So these are parallel and they lie on top of each other. So this is parallel and they lie on top of each other. So not only now are they sharing a direction vector, but they also have all of their points or an infinite number of their points in common. And that could look something like this. So we have our first vector, which is represented by a position vector, negative 1, 4, negative 2. Plus some scalar multiple of the direction vector, negative 2, 1, negative 3. And then we could have a second line represented by this vector equation of 1, 3, 1 as my position vector, plus a scalar multiple of my direction vector. It could either be a scalar multiple of the direction vector from line A, or could be exactly the same. So again, they share a direction vector. They don't necessarily share this point, this position vector, but if we were to dive into this and do a little investigating mathematically, we would be able to prove that they do share all of their points. And we're going to talk about that in a little bit. Now let's talk about the other two choices. Let's talk about if they're intersecting or if they're skew. So if they're intersecting, they're not parallel, but they're on the same plane in 3 space, just meaning that they're lying on the same. If I were to put a piece of paper and create a plane, and I know we haven't talked about planes yet, that's coming up in the next lesson, but if I were to draw a flat surface that went along the direction of both of these, both of these lines would lie right along there. So they're not parallel. We can say they're not parallel. And I think we can see that from the diagram. They're not parallel, but they are on the same plane. They are on the same plane. They're not going anywhere. They're not going on a trip. They just happen to be on the same level. You can think of it as on the same level. And this could be represented with a vector equation. Let's say we have a position of negative 3, negative 2, 4, plus a scalar multiple of some direction vector. And then we have another line that's represented by a vector equation of negative 3, negative 2, 4, plus a scalar multiple of some direction vector. Now, make note here that these direction vectors are not the same. So we know that these aren't parallel. They're not scalar multiples of each other. The direction vectors don't match. So these two lines we know are not going to be parallel to each other. But we can see here that they actually do share a common point. So they share one point in common. So they share one point in common. And just like in 2 dimensions, that's the point of intersection. There's one point of intersection. Now, when we start doing these examples, it's not going to be as obvious as both lines having a vector equation that has the same position vector. Where would the fun be in that? But I think we already can see that we can determine if a point lies, if there's one point that lies on another line. And that's actually what we're going to look at to try and prove that today. The last one that we're going to look at is skew. I'm just going to make that a little bigger, and I'm going to try and squeeze some stuff in here. So these are also not parallel, and we can see that in this drawing. So these are also not parallel. But the difference between parallel, not parallel, and one point of intersection and skew is that these aren't parallel, but they also will never meet. Not parallel, but will never meet. that can be hard to visualize. So we could have an example here again where we have a vector equation of -3, position vector -3, -2, 4, plus some scalar multiple of our position 1, 1, 1, and a second line or vector with a position vector of 2, 5, 4, plus a scalar multiple of some direction vector. We can see that these are not scalar multiples of each other. The direction vector is not a scalar multiple, so these are not going to be parallel. What our job would be to determine if they do have any point in common or not. If they don't have any points in common, then they are going to be skewed. If they do have a point in common, then they're parallel. They have a point of intersection. They intersect. Okay, so they don't share any points. This is different than two space. And I think it's hard to think of it. It's hard to visualize it. So we're going to pop over to GeoGebra to actually take a look at what this looks like in 3 dimensions when they're graphed. Okay, so here are those two lines graphed out. We can see when we're looking at them, they appear that they might be intersecting, but if I were to rotate this image around, we can see that they actually don't cross over. I hope you can see that these are never going to cross over. These are skewed lines. They are not parallel, but they will never cross each other. And that's the difference between intersecting lines that are not parallel and skewed lines that are also not parallel, but will never meet in that third dimension. Okay, so let's do a 2D example. So in 2 space, remember, we have 3 choices for what could be happening. They could be parallel. And if they're parallel, we have 2 choices. They may never meet, or they could be coincident, which really just means they share all their points or are the same line. Or the other option that we have here, or they could just be not parallel. And if lines in 2 space are not parallel, then they must meet at a point of intersection. So here we have 2 equations. We have a symmetric equation, and we have a regular old vector equation, symmetric and a vector equation. So the first step with this is always going to be to check to see if the direction vectors are parallel. And remember, the direction vectors will be parallel if they are scalar multiples of each other. So for my symmetric equation, I can just look at what's on the bottom of the fractions, and that will tell me that for line 1, my direction vector is 4, -1. For line 2, my direction vector is this part right here, and this tells me that this is -8, 2. So if we take a look at these, we can see that they are actually scalar multiples of each other. So now we have to decide, are these parallel or are they the same? Are they parallel or the same line? Okay, so now we need to determine, are they parallel, no points in common, or are they the same, all the points in common? So if we think about this for a second, we know that we can prove if they share 1 point, then they will share all of their points. That's really the nature of parallel lines. If they don't share even 1 point, then they're not going to share any. So we're going to use some geometric thinking to check if 0.15 from line number 2, if 0.15 from line number 2 is going to lie on line 1. So line 15 from equation 2, will it lie on line 1? Okay, so we know that we can prove that they share one point, that they will share all their points. Like I say, that's the nature of parallel. So we're going to use our geometric thinking to check if this 0.15 from equation 2 lies on line 1. So the first thing that we're going to do here then is set up the parametric equations for line 1. So just as a reminder, the parametric equations, just break it down into its x and y components. So this is the parametric equation for line 1. So for line 1, we have x equals 3 plus 4t. And for y, our y coordinate, we have y equals -2 minus t. Okay, so now let's check the 0.15. So if x equals 1, what does t equal? Rearrange and solve, we get -2 equals 4t. So t is going to equal -1/4. Now, if they are the same value, then the point lies on the other line. If they're not the same value of t, then they do not share that point, which means they are not parallel. So let's finish this one out. So if y equals 5, then 5 equals -2 minus t. This becomes 7 equals -t. So this t value is -7. The t values are different. Therefore, 1,5 does not lie on line 1, so we can say, therefore, the lines are parallel and distinct. Lines are parallel and distinct. And I'm just going to add back in there that the t values are different. That's how we know this. T values are different. So 1,5 does not lie. Should have given myself a little more room here. Hold on. Does not lie. Let's see if I grab this and move it down. Grab this and move it down. I'm not having much luck just grabbing this and moving it down, but there we go. Grab that and move it down. Okay, so the t values are different, so 1,5 does not lie on line 1. Because it doesn't lie on line 1, then none of the points are going to lie on line 1. Now let's look at some 3D examples. And remember, we have more choices when we have 3D. So things can still be parallel. So we could still have two parallel lines, and those two parallel lines could be distinct, meaning they never meet, or they could also be coincident, or the same. They could lie on top of each other. That is a possibility. Or they could be not parallel, same as before. However, now in 3D, if they're not parallel, there could be one point of intersection, one place where they meet, or now we have this skewed, meaning that they never meet. So they could be not parallel, but they could never meet. And in 2D, that doesn't happen. If they're not parallel, then there will be some point where they will cross each other. In 3D, that doesn't happen. So again, we're going to start by checking the direction vectors to see if we have parallel lines. Now this time we have two parametric equations, and the direction vectors will be just the coefficients that are attached to the scalar multiple for each equation. So for line 1, we have a direction vector of 3, 2, 6. For line 2, we have a direction vector of 1, -5, -1. So I think we can see that they are not going to be scalar multiples of each other. So therefore, they're not parallel because they are not multiples. Therefore, there must be one point of intersection or they never meet. So must have one point of intersection or never meet, meaning that they are skewed. Okay, so how do we tell? Well, we're going to start by solving the system. So we're going to set x, y, and z parameters for each equation for each line equal to each other. And then we're going to solve using either substitution or elimination. So let's come down and let's do that. So for our x value, if we set both of these equal to each other to create equation 1, we are going to have from line 1, we're going to have -5 plus 3s is equal to t. For our y value, this is going to give us equation 2. We have 2 plus 2s is equal to -6 minus 5t. And for my z value, we are going to have -7 plus 6s is equal to -3 minus t. So we've set those all up. Taking a look at them, Taking a look at them, I'm going to determine that I'm probably going to do a substitution, but we're going to get to that in a second. So two things could happen with these set of equations. We could get one set of values for s and t that work for all three coordinates. That would mean we have a single point of intersection. Or we could get a set of values that only works for two of the three sets of the equations. This would make it skewed. So we're going to pick two equations and solve using substitution or elimination. Since equation 1 here is just equal to t, so t is equal to -5 plus 3s, I'm going to use substitution and I'm going to sub equation 1 into equation 2. And hopefully I have enough room to do this. So substituting equation 1 into equation 2, we get 2 plus 2s is equal to -6 minus 5. I'm going to substitute my t value in of -5 plus 3s. Now I'm just going to expand, simplify, and solve for s. So we end up with, just doing some rearranging, I get 2 plus 2s equals -6 plus 25 minus 15s. Get all the variables to one side, all of the numbers to the other. I get 17s is equal to 17. So s is equal to 1. There's our value of s. Now we're going to take that value of s and sub it into equation 1 to solve for t. So now we're going to sub to solve for t. And so we have -5 plus 3 times 1 is equal to t. All I've done is I've taken that s value of 1 and substituted it in. That gives me -5 plus 3 is equal to t. So t is equal to -2. Okay, so we now have our two distinct s and t values. Now, because we have that third, our z value, we have our third coordinate, now we have to check if the left side equals the right side for equation 3. I've just copied this over onto another page just so we have a little bit more room to work with. So like I say, now we're going to check if left side equals right side for our third coordinate, or as we've been calling it, equation 3. So just as a reminder, our equation 3 would be -7 plus 6x on one side equals -3 minus t on the other. So we have -7 plus 6s on the left side, and we have -3 minus t on the right side. Substituting our values in, we get -7 plus 6 times 1 equals -7 plus 6 equals -1 on our left-hand side. Now let's substitute t in on our right-hand side. -3 minus -2 equals -3 plus 2, which equals -1. My left side is equal to my right side, Therefore, there must be one point of intersection. Therefore, one point of intersection. To find the point of intersection, we're simply going to sub t equals 2 into line 2 because that has t in it. You could sub s equals 1 into line 1 as well. Same idea. So to find the POI, sub either s equals 1 or t equals -2 into the appropriate equation. I think I spelled that wrong. Hold on. Into the appropriate equation. So we are going to use t equals -2 because that's what I said we were going to do. So if x equals t in equation 1, because we had, in equation 2, so this is our equation, this is our line 2. We're going to sub it into line 2. So if we have x equals t, and we know that t is equal to -2, then there's our first coordinate. Y in that one was -6 minus 5t. So y will equal -6 minus 5 times -2. So y will be equal to -6 plus 10. So our y value at our point of intersection will be 4. And our z value, our z equation was -3 minus t. So z will equal -3 minus -2. So z will equal -3 plus 2. So z is equal to -1. So this is telling me that my point of intersection for this particular set of lines will meet at -2 for -1. So this is our first example of two lines in 3 space that do not have, they're not parallel. However, they do have a point of intersection. So let's take a look and see what this looks like if we graph it in 3D. Okay, so here it is graphed in 3D. You can tell it's very difficult to tell whether that is actually a point of intersection or not. But if we manipulate this and look at it from all angles, we can actually see that they are crossing over. Okay, let's try one more 3D example. What I'd like you to do is pause the video, give this one a try, and then come back once you've solved it to see what it looks like, to see what the solution looks like. Okay, so if you are back, I'm hoping that you've gone ahead and taken a look at it. So remember, the first thing that we want to do is determine are they parallel or not. And we're going to do that by taking a look to relate the two. I'm actually going to do it up here so I have a little more room. We're going to take a look to see if our direction vectors are the same for both. So we have a direction vector for line 1 of 1, 3, 7. We have a direction vector for line 2 of 5, -4, 2. Okay, so D1 is not a scalar multiple of D2, therefore they are not parallel. So now we need to figure out, is it a point of intersection or are they skewed and destined to never meet? So now at this point, we need to create the parametric equations for each line so we can set up the system of equations. So for line 1, our parametric equations will be x equals -2 plus t, y equals 1 plus 3t, and z is equal to 7t. -2 plus t, 1 plus 3t, 0 plus 7t. For line 2, we have to think about it a little bit more because this one is our symmetric equation. So remember, x will be equal to the opposite of the value on the top. So x will be equal to 3 plus our direction vector on the bottom, 5 times s. Y will be equal to negative 3 minus 4 times s. Now, z, we have to think about. Okay, so we have 4 minus z over 2. This really is telling me that I have, oh, I don't know why it's doing that. Okay, that we have, if I rearrange this to make the z positive, I have z minus 4 over negative 2. Doesn't change the fact that our direction vectors are still not scalar multiples of each other. It's simply changing what we have on the top versus what we have on the bottom. So we end up with z equals 4 minus 2s. Okay, let's say this is our equation 1. Here's equation 2. Here's equation 3. So we're going to pick any two of those equations and solve for t and s. And since we used substitution last time, let's use elimination for this one. So I'm going to choose to use equation 1. And equation 1, if we equate the two of them together, negative 2 plus t is equal to 3 plus 5s. And we'll use equation 2. That is equal to 1 plus 3t equals negative 3 minus 4s. So I can't subtract right away. I have to manipulate equation 1 because we're going to eliminate t and solve for s first. In order to do that, I need 3 t's on the top, which means I need to multiply equation 1 by 3. That means I'm multiplying everything. And I know you guys know this. I'm just reminding you. So negative 2 times 3 is negative 6 plus 3t is equal to 3 times 3 is 9, plus 5 times 3 is 15s. We're not making any changes to equation 2, so we still have 1 plus 3t equals negative 3 minus 4s. We are going to eliminate, and we're going to use subtraction. So 6 minus negative 1 gives me negative 7. 3t minus 3t is 0. 9 minus negative 3 becomes 12. And 15s minus negative 4s becomes 19s. Rearrange and solve, and we end up with s equals negative 1. Now that we know our s value, we're going to sub this into 1 to solve for t. So sub into 1 and solve for t. So equation 1 was negative 2 plus t equals 3 plus 5 times negative 1. So t is equal to 0. So now that we know the s and the t value, we need to go ahead and we need to check the left side, right side for that third equation. In order to determine if there is a point of intersection or not. And if there is a point of intersection, remember the left side will equal the right side. If there is not a point of intersection, then the left side will not equal the right side. So we're going to check left side equals right side. And we have 7t equals 4 minus 2s. This equals 7 times 0. Our t value is 0. So our left side equals 0. My right side, when we substitute s is equal to negative 1, we get 4 plus 2, which means that my right side is equal to 6. My left side does not equal my right side. Therefore, there is no point of intersection between these two lines. They must be skewed. One more trip over to GeoGebra to take a look at this. So here are these two lines graphed in 3 dimensions. If we take a look, it is hard to tell. It almost looks like there could be a point of intersection down here. But if I manipulate this so that we spin it around, we can see that these actually do not cross each other. They are actually skewed. You could also have verified that there is not a point of intersection algebraically by subbing t equals 0 and s equals -1 into lines 1 and 2. If there is a point of intersection, the coordinates will be the same for both. No point of intersection means they're skewed, and the coordinates will give two different points. I went ahead off camera and just did that math. So to verify again that there's no point of intersection, we're simply going to substitute our values of t equals 0 and s equals -1 into the appropriate parametric equations. When we substitute t equals 0 into line 1, we get a point of -2, 1, 0. Verifying with line 2, when s equals -1, we get a point of -2, 1, and 6. So there is no common point of intersection, therefore these lines are skewed. Okay, that's it for today. So hopefully now you can identify if there is an intersection between two lines in both 2D and 3D. Not a lot of homework questions for tonight, just 2 questions, 4 and 5 from page 471. If you have any questions, feel free to send me an email.